Hello everyone, welcome to Concepts in Chemistry YouTube channel and also welcome to the Chemistry Concept Booster series. So today in this video we will be discussing some questions from organic chemistry. So yeah, I think about 15 to 18 days ago, that is a long time ago, we uploaded 3 or 4 videos, and in those videos we have discussed about 18 or 19 questions from organic chemistry. So after a long time back, we came back with organic chemistry question answer discussion. So yeah, let's start the discussion without any delay. So chemistry concept booster question number 34. So in the chemistry concept booster series, this is the question question number 34, and I think if we count the organic chemistry questions, so it will be around 20 or 21 number questions from organic chemistry, and overall chemistry concept booster question number 34. So let's discuss. So this is the questions. So this is a tetra substituted cyclohexane compound. These are the reagents: paratoluene sulfonic acids, then TBACl, catalytic amount of DMAP, triethylamine, tetrabutyl ammonium iodide, DMF. These are the reagent conditions. So if you see guys, then you can see in the every options there is stereochemistry mentioned. So we have to take care about the stereochemistry during our mechanism. So let's see the mechanism in details, then we will see the options. So this is the tetra substituted or cyclohexane 1 2 3 4 5 3 4 5 triol carboxylic acid. So yeah, 1 2 3 1 3 4 5 tetraol carboxylic acid, cyclohexane carboxylic acid. This is the moieties. So if we draw the this cyclohexane in chair form, then we can see this carboxylic acid is above the plane, so it is in axial position, it should be, and the hydroxyl group at 3 positions, this also above means axial, and this other 4 5 and also 1, these 3 should be in below. So this equatorial, this is equatorial below, and this 4 1 is axial, that is below the plane. So this is the chair form of this moieties. Now we are treating with this molecule with paratoluene sulfonic acid, toluene solvent and reflux. So we know if there is any connectivity like carboxylic acid along with some hydroxyl group, then there is possibility of ester formation. So this is since this is a cyclic ester, so that is called lactone molecule. So we can call this step is the lactonization step. So esterification, cyclic ester we called lactone. So see in this molecule we can see here that 4 hydroxyl group and 1 carboxylic acid group is present. So the hydroxyl group cis orientation with the carboxylic acid, that will take part only this esterification or lactonization process. So the other this is, yeah, obviously this OH will not take part in this lactonization process, because this OH is same attached with same carbon where the carboxylic acid group is attached. But see this axial OH at 4 position and at 5 position, they are in not cis position along with this carboxylic acid group. These are also this OH group are far away from this carboxylic acid. So this carboxylic acid react with this 3 OH group via removing of water molecule to form cyclic ester or lactone. So in this step, lactonization take place between the carboxylic acid and the OH group which are in cis manner. So this carboxylic acid and this OH group at 3 positions means this will take part in lactonization process. So after this step, we obtain this molecule. Now we are using TbHCl, catalytic amount of DMAP, catalytic amount of tetrabutyl ammonium iodide, DMF. So this is just a alcoholic OH protection reactions. We all know that we usually use TbHCl for OH group protections. Now see, in this molecule there are 3 OH group free. One is this equatorial attached with a 3 degree carbon. This is a OH equatorial attached with a 2 degree carbon. This OH is axial attached with a 2 degree carbon. So if and we are using 1.2 equivalent, means only one OH group will protect, will react with this TbHCl to form OTBS. If this axial OH become OTBS, then since it is axial, then after protection it become OTBS, the size of this group, whole group, become large and it will suffer from severe 1,3 diaxial interaction. We all know that axial group suffer from 1,3 diaxial interaction. So that's why this OH group cannot convert into OTBS for these reactions. If this OH, see, already this OH, surrounding of this OH is so much congested or so much crowding is there, means this carbon is 3 degree on. One carboxylic acid group is there and 3 carbon chain is and 2 carbon chain is added. Already this carbon is so much congested. So if this OH become OTBS, still it is a equatorial, but when it become OTBS, then it will suffer from some severe steric repulsion. In this case, not 1,3 diaxial interaction, but severe steric repulsion, because this is a 3 degree carbon, 3 substituent already is there, and this OH when become OTBS, there is severe steric repulsion between the substituent. So that's why this OH also not react with TbHCl to form OTBS. See, in this case, this is a equatorial. If this OH become OTBS, there is no chance for 1,3 diaxial interaction. Again, this is a 2 degree carbon where the OH group attached. So when this OH become OTBS after reacting with TbHCl, then there is no such crowding or steric repulsion like this OH group. So only this 2 degree equatorial OH react with this TbHCl to form OTBS. So now we obtain this product. If we again redraw this compound, we can see this is the actual product. So yeah, 1 or 2 points you have to keep in mind that if they ask about, if we consider this step and if they ask about reaction rate of TBS formation, OH become OTBS. So OH become OTBS, that is TBS protection reaction. If we calculate the rate, then 2 degree equatorial OH, this OH react faster, then this axial 2H, axial 2 degree OH, then equatorial 3 degree OH. So it indicates that if we use 2 equivalent of TbHCl, then this 2 degree equatorial OH and this 2 degree axial OH react with TbHCl to form di-OTBS. This OH will not react. This is equatorial, but since there is so much crowding already present, that's why this O when become OTBS, there is severe steric crowding, steric repulsion will be there. That's why the reaction rate of this TBS protection step is first for 2 degree equatorial, then 2 degree axial, then 3 degree equatorial. And they used here that tetrabutyl ammonium iodide for just in reaction medium TbHCl is there. So in presence of this tetrabutyl ammonium iodide, more reactive species TbSi will form. And we all know I is a very good living group, so they use this salt to form a more reactive species TbS iodide in the reaction medium. So these are the some points. Yeah, now see, this OH attached with the carboxylic acid group is free. 1, 2, 3 OH take part lactonization via same phase. 4 OH should be free. 5 OH become protected with TbHCl. Now see the options. So in all the options, this lactone are in the same phase, means that is correct. But in this option B, this OH become OTBS, that is not correct. This is also not correct because this double bond is there. and in the C options they showed here the protection in 4 OTBAs, that is these 4 axial OAs. So only option A is correct. If you see the structure of this compound, see, if this is 1, this is 2, this is 3 carbon, 4 OH will be free, 5 OH should be protected as OTBAs. So the correct option for this reaction is option A. In this case, we have to take care about stereochemistry as well as the this protection step. There are 3 OH group remain free. So if we are use 1.1 equivalent or 1.2 equivalent, then only one OH group protect, that is the 2 degree equatorial. If we use 2 equivalent, that is, or that some excess of 2 equivalent means 2.4 or 2.5 equivalent, then only this 2 degree equatorial and 2 degree axial OH group will protect. And this is the rate of TBS protections: 2 degree equatorial, then 2 degree axial, then 3 degree equatorial. So yeah, I think you all understood the whole mechanism, the stereochemistry, the cis OH and cis carboxylic acid will take part in the electronization process. So yeah, let's move to the next question. So before discussing the next question, just I wanted to mention you that by solving this different kind of organic question from organic chemistry, so we will cover all the topics from organic chemistry subject. So I think this is the only way or effective way to improve your organic chemistry question solving power. Just solve or discuss or practice as much as possible organic chemistry question from different type of organic chemistry question. If you solve different type of organic chemistry, then you will know what is the use of reagents, and in every reactions there will be involvement of name reactions, rearrangement, pericyclic reaction, use of reagent, that is oxidizing agent, reducing agents, so many things you will be aware about all these things. So particularly in organic chemistry questions, when we will discuss, already we discussed some questions in this video, we are discussing some more. Again, our upcoming videos we will be discussing lots of organic chemistry questions, and in this way we will cover all the syllabus, that is we will cover by solving these reactions all the syllabus like name reactions, rearrangement, or use of reagents, pericyclic reactions. So yeah, so according to me, this is the proper way or effective way to improve the organic chemistry question solving power. So let's discuss the next question. So yeah, see these questions. This is a bromide, cyclic bromide, but if you see this function that is allyl bromide, and these are the reagents: thioacetyl anion, sodium ethoxide ethanol, then alpha beta unsaturated nitro compound, then phenyl isocyanide, then lithium aluminum hydride. In this question also we have to take care about the stereochemistry. See, in the option stereochemistry is there. So yeah, let's discuss the answer with details. So we all know that allyl bromide is a perfect substrate for nucleophilic substitution reactions. This is the nucleophile. If it attacks directly this carbon containing bromine center, then it is called SN2. It can attack also by at these positions, then it will be called SN2 dash reactions. So we will get same product, either it will attack by SN2 or SN2 dash, we will get same product. So we all know that allyl and benzyl halide are, particularly bromide, are very susceptible towards nucleophilic substitution reaction. So if it react with SN2 or SN2 dash, we will get same product, that is so yeah, now we obtain this product after this substitution reactions. Now sodium ethoxide base will attack this carbonyl carbon to release this anion. So now this anion attack with this alpha beta unsaturated nitro compound like a alpha beta unsaturated carbonyl compound via 1,4 addition. So yeah, you can assume this as a carbonyl functionality, and this is the alpha beta position. So this nucleophile sulfur nucleophile will attack this beta position to obtain this kind of intermediate. Now this negative charge will push back and this bond will break. It will abstract on H plus from reaction medium to form this nitro compound. Now we just for our drawing purpose, for simple drawing purpose, we just assume this whole ring as a R group, and now this if we draw the resonance structure of the NO2 group, this will be this. Now this O minus attack this phenyl isocyanate, carbonyl carbon of the phenyl isocyanate, then it will form this compound. Now this O minus negative charge push back, this double bond break, and it will abstract on hydrogen from this carbon. Means from this carbon it will attack on hydrogen, then this intermediate will form. Again this NH, after breaking this bond, it will become PH NH. This lone pair of NH abstract another hydrogen from the same carbon, means this carbon, it will form a triple bond. This bond will break, this bond will break. So in this step, carbon dioxide and aniline molecule release from this moieties, and at last we obtain a nitrile oxide kind of moieties. So these all steps we are performing here to obtain at last a nitrile oxide. So nitrile oxide, it is a very good substrate for cycloaddition reaction. So nitrile oxide we can say is a 1,3 dipolar compound. How? See, 1, 2, 3. If we break this bond like this, in this way, if you break this bond like in this way, then here will be positive charge, nitrogen become neutral, and this is negative charge, means 1, 2, 3. So 1, 3 dipole, we can say this is a 1, 3 dipole. So just this is a stable structure of 1, 3 dipole. If we break one of this bond, then it will become positive charge in this carbon, nitrogen become neutral, and O minus as same. So it's a 1, 3 dipole is a perfect substrate for cycloaddition reactions if there is present any alkene or alkyne group. Now see, this is nitrile oxide, and if we draw again the ring, in the ring on double bond is present, so it will take part in cycloaddition reactions. So now after cycloaddition reaction 1, 3 means this bond will attack this one positions, this bond will break, and these 3 positions will attack again the double bond of the other side. So we will get this kind of product after 1, 3 dipolar cycloaddition reactions. See the stereochemistry. Both the product are formed, means either it is like this, all the ring hydrogen are in cis positions, or all the ring hydrogen are in below. Should be cis, the ring hydrogen should be cis, but either above or below. If we consider this transition state, means hydrogen is above, the sulfur of or this all substituent become below, or after ring formation the hydrogen of this bond and these positions should be same as this hydrogen, means hydrogen should be above and all the substituent become below the plane. If we consider this transition state, then see the hydrogen is below, the sulfur substituent containing this nitrile oxide will be above. Again after ring formation, the hydrogen of this carbon and this carbon become same, stereochemistry of this hydrogen become same as this hydrogen. That's why if we consider this structure, the hydrogen of the ring junction are below, but all are in cis positions. In this case the hydrogen are above the plane, still all are in cis positions. So see in the options, the ring hydrogen, see in the 4 options, these are one above, one below, both above, both above. So we have to consider this product or this product. If in the options the ring hydrogen in below, both below, then we have to consider this structure. But since in the options there is no options for ring hydrogen are below, in two options ring hydrogen are above and other two options one above one below. So we have to consider this compound for further reactions. So now they are using at last lithium aluminum hydride. So lithium aluminum hydride first attack this imine carbon from the side where the hydrogen are projected. So this C is hydrogen are above the plane, and in the below this whole substituents are in the below the plane, means the below phase is more crowded. That's why hydrogen attack from the top side, same side as this hydrogen are projected. So after these reactions this hydrogen become top side, because it attacks from top side, it will this hydrogen will above the plane and this NH should be below the plane. Now again from in presence of lithium aluminum hydride, this NH bond will break. NH bond will break to form NH2 and OH. So after finally we obtain this kind of product. So the ring junction, this hydrogen are cis but above the plane. This hydrogen is above means this OH should be below. That's why we are mentioning here OH, not mentioning the stoichiochemistry of hydrogen and in that carbon. We just mention the stoichiochemistry of OH below, means obviously the hydrogen should be above. Same case, this in this case this hydrogen is above means this NH or NH2 should be below. We are just mentioning here the stoichiochemistry or showing the stoichiochemistry of NH2 below, means the hydrogen should be above. So see the options. The ring junction hydrogen should be cis, either above or below, but in the other options one above one below is there, so these are not the correct answer. In this case both are above the ring junction hydrogen, so among these two one is correct. Now see the OH and NH2 stoichiochemistry. The OH and NH2 stoichiochemistry are seen to each other, but opposite to the ring junction hydrogen. So the NH2 and OH are seen stoichiochemistry to each other, but opposite stoichiochemistry to the ring hydrogen. So the option is A is correct. In this case NH2 and OH are opposite stoichiochemistry. So see the product, OH and NH2 are seen to each other but opposite to the ring hydrogen stoichiochemistry. That's why this is the correct answer for this reaction. See in this case, just for synthesizing a nitrile oxide, which is a good partner for 1,3-dipolar cyclization reactions, we did here this much reactions. So in this case cyclization reactions and use of lithium aluminum hydride reagent, we learned just some pre-cyclic reaction, means cyclization reactions, lithium aluminum hydride, use of lithium aluminum hydride. So yeah, now the product is this. So let's move to the next question. So yeah, in this questions allylic alcohol is given and this is the reagents. So potassium hydride, then gamma beta gamma unsaturated aldehyde compound, then heat. These are the options. So in this case there is no mention about stoichiochemistry, so no need to concentrate about stoichiochemistry. Just we have to focus on proper mechanism, actual mechanism. So let's see the answer with details mechanism. So allylic alcohol, in presence of base, this OH become deprotonated. This O minus now attack this carbonyl compound to form this kind of intermediate. Now after acidic workup, this OH O minus become OH. After heating, this H and OH combine, this OH and H combine to remove a water molecule. Now we are getting this kind of product. Now see this, if you carefully see this compound contain allyl vinyl ether functionality. This is a vinyl ether and this is a allyl ether molecule or functionality. So we all know that if there is a compound containing this kind of functionality, allyl vinyl ether, then there is a chance for Claisian rearrangement reaction or sigmatropic 3,3 sigmatropic rearrangement reactions. So yeah, this is 1, 2, 3 carbon, this is 1, 2, 3, So in this 3-3 sigma-tropic rearrangement, the bond between 1 and 1, so this 1 carbon and 1 oxygen, this bond will break and the new bond will form between the 3 and 3 member. So after sigma-tropic rearrangement, that is Claisen rearrangement for this case, we will get this product. New bond will form between 3-3 and the bond between 1-1 will break. If we again rotate this molecule and redraw like that, then again this, see there is a functionality like 1-2-3 1-2-3. Again this molecule can undergo a second 3-3 sigma-tropic rearrangement, and this 3-3 sigma-tropic rearrangement is also called as Cope rearrangement. So then again this bond between 1-1 will break and new bond form between 3-3. Now we will get this kind of product. This product is named as citral. So see, just removing of A's from OA's, we will get after acidic workup and after heating this product, and just after heating this compound will take part a sigma-tropic 3-3 sigma-tropic rearrangement, that is Claisen rearrangement. Again this product, again this compound will take take part another rearrangement, that is also a 3-3 sigma-tropic rearrangement, that is called Cope rearrangement. At last we will get this product. So in this case, two sigma-tropic rearrangement take place, that is both are 3-3 sigma-tropic rearrangement, but one is Claisen and another is Cope rearrangement. So this type of questions may be asked in a different way. So if they give the product and the starting material, then what is the reactions we will get this product via which kind of reaction, sigma-tropic, or the option may be like 2-3 sigma-tropic, 3-3 sigma-tropic, 1 sigma-tropic, or 2 sigma-tropic reactions. So in this way these questions can be asked or can be set in competitive exam in different way. So see, again we are saying here that so many sigma-tropic rearrangement, that is pericyclic rearrangement. So the correct option, if we see the options, so option C is correct, because CHO double bond methyl CH2 double bond 2 methyl, CHO double bond methyl CH2 double bond 2 methyl, these are the not the correct options. So in this case double bond is not here, but double bond should be in this place. So if you stop in this compound, if you will get wrong product for these reactions. Since this product there is a functionality which can take part another cyclization, another sigma-tropic rearrangement, then yeah, it will proceed again another cyclization reaction to form final this kind of product. So this one is Claisen rearrangement, this one is Cope rearrangement. So the option is C option is correct. Again move to the next question. So yeah, again allylic alcohol is given. Now these reagents are different. Pa is HCl, pyridine, butyl lithium, BNBr means benzyl bromide, and that phosphide and methanol. These are the options. Again there is no mentioning about stereochemistry. So let's discuss the reaction mechanism with details. So in the question C, pH is given and BNBr is given. pH and BNBr means PaCH2Br, benzyl bromide. So in the reaction mechanism we just write here R and R dash. So R is pH and R dash is CH2pH. So this allylic alcohol will attack this sulfur. This is a electrophile. This is a nucleophile. So now this will form, pyridine will abstract this hydrogen from this moieties, then we will get a sulfonate ester. Again if you see the functionality, you can see this oxygen and sulfur 1 2 if we mark, and this carbon 1 2 3. If you study, I think we all know that sigma-tropic rearrangement there are 3-3 2-3 sigma-tropic rearrangement. If you study 2-3 sigma-tropic rearrangement, then you can easily see this type of connectivity will be there. So again this is a 2-3 sigma-tropic rearrangement. So the bond between 1-1 will break and new bond will form between 2 and 3. Now the bond between sulfur and this carbon will form. This is the allylic sulfoxide. Sulfonate ester after 2-3 sigma-tropic rearrangement form allylic sulfoxide. we are using butyl lithium in the next step, this hydrogen of this carbon become more acidic because this is a allylic position, and also on SO-pH group electron withdrawing group is there, that makes this hydrogen more acidic. In presence of butyl lithium, this hydrogen will abstract and form an anion. This anion now attack this BNBr, that is R dash. PaCH2Br we all know is a very good electrophile in substitution SN2 substitution reaction. This anion attack this CH2Br, that is just a simple R dash Br. We mention here R dash means CH2PH to form like this molecule. Again we can see here is a functionality like 1 2 3 1 2. Similarly like this 1 2 SO single bond, here SO double bond is there. So again 2 3 symmetry rearrangement take place. Now the new bond between 2 and 3 will form oxygen and this carbon, and the bond between 1 and 1 will break. So we will get at last this kind of product. Now this phosphide molecule attack this sulfur to release this anion. Now this anion will abstract one hydrogen from solvent to form this kind of allylic alcohol and O minus, and this OMe react with this intermediate or this phosphonium salt to release a trimethoxy what is the name, this so this I forgot the name of this molecule. So this P double bond O is a very stable bond, that's why this molecule will form along with PHMe and some side products. So the expected product of this reaction is this allylic alcohol. These are the side products. This is called phosphonium oxide. So this is a stable molecule because of the P double bond O, a stable bond. So see, in the starting material allylic alcohol is there, only one substituent with this terminal double bond. Now after all these reactions, 2 symmetropic rearrangement, that is 2 3 symmetropic rearrangement, deprotonation, then again again base, again attacking of that electrophile like PaCH2Br benzyl bromide. See, at last we will get we obtain same product, same allylic alcohol, just now become doubly substituted. This terminal carbon of this double bond part become doubly substituted. So we are performing all this reaction here just to bring another substituent in that terminal carbon. So first R is there, means pH is there, now R dash come means CH2PH come in the same alcohol. See, no change in the alcoholic positions, just in first case one substituent is there, now there are second substituent, means this is more substituted, this is doubly substituted allylic alcohol. So if you see the options, this is not correct, this is also not correct. So at terminal position the pH and CH2PH should be there. pH means R and CH2PH means R dash. Same allylic alcohol with doubly substituent at terminal position, not the middle positions. So this is also not the correct product. So the correct option of this reaction is option C. We are doing all these reactions to bring extra one substituent in that positions. See, this is the chemistry. So yeah, let's move to the next questions. So yeah, this is called pyrrolidine molecule. If double bond is there, then that is pyrrole, and this is the saturated version of pyrrole, means pyrrolidine. We can call N-ethyl pyrrolidine molecule using MCBA heat, then mercurous oxide, styrene, zinc acetic acid. So these are the options. In option stereochemistry is there, so we have to take care about the stereochemistry during mechanism. So yeah, N-ethyl pyrrolidine in presence of MCBA, just it's become N oxide like pyridine, when we react with MCBA or H2O2, it becomes pyridium N oxide, that's oxidation. So same pyrrolidine N-ethyl pyrrolidine react with MCBA to form N-ethyl pyrrolidine N oxide. Now after heating, this O minus will abstract this hydrogen. If we draw properly this ethyl molecule CH2CH3, CH3 means CH2H, it will abstract one H from this, and this bond will break, this bond will break. Just one ethylene molecule will release from this compound and just form a N-hydroxyl pyrrolidine molecule. So now this is a neutral N-hydroxy pyrrolidine molecule. We are using again molecular oxide. So yeah, not this is mercury oxide, not mercurous. This is mercuric oxide for oxidation. So see, one hydrogen is removed from this place and one hydrogen from this place. So removal of two hydrogen means also oxidation to form a cyclic nitron. So see, this is also a 1,3 dipole. We can say 1,2 position we are showing the dipole, but if we break this bond like this way, nitrogen become neutral, positive charge become this position. So 1, 2, 3, 1 positive charge, 2, 3, 3 negative charge. So that is called 1,3 dipole. So this is a perfect substrate for 1,3 dipolar cyclization reaction. We just saw some time ago in the previous questions. If there is an alkane or alkyne, it will react with this alkene or alkyne via 1,3 dipolar hydrogen reactions. So now see, this pH should be XO means this double bond, not the side of this double bond. This pH should be XO to release the steric repulsion. So this if this pH is that side, means this hydrogen is C in the side of double bond and pH is far away from the double bond, that is pH should be XO, otherwise there will be steric hindrance. In the product after cyclization reaction, see, this hydrogen is same side as this pH. So after cyclization product, we have to take care about the stoichiometry of this hydrogen and this pH. This hydrogen and this pH should be same, should have same stoichiometry. That's why we draw here H and pH above the plane. So this pH and this hydrogen, ring hydrogen, are same side. If we imagine like that, this bond is left side or this H is right side. Again for this styrene, this hydrogen is left side, this pH is right side. So after cyclization reactions, the stoichiometry of this hydrogen and this pH should be same, should have same stoichiometry. That's why this hydrogen and this pH we have shown here same stoichiometry, that is above the plane. So yeah, you can XO means this pH should be far away from the double bond, and you can also draw like this hydrogen and this pH are below. So yeah, that is also possible. This hydrogen and this pH should be below means below the plane, but this H and this pH should have same stoichiometry, either below the plane or above the plane should have same stoichiometry. So here we shown the above the plane. So and we are using next zinc acetic acid to just break this NO bond. NO bond, after breaking, this become NH and this become OH. So yeah, if you can remember, see the last questions. We are using lithium aluminum hydride for NO bond breaking. They used in this case lithium aluminum hydride to perform two reactions. One is attacking of this imine bond to form this simple amine. Now after that, again that same lithium aluminum hydride will do the same another work, the NH bond breaking, to form this NH2 and OH. So in this case they use zinc acetic acid. So zinc acetic acid for this NO bond breaking. So yeah, In this case, also lithium aluminum hydride can used for this bond breaking, but yeah, since on phenyl ring is there, that may create some problem. So, but zinc acetic acid, if they used in that reactions, then only if in this reaction they use zinc acetic acid, then only this reaction will be done by zinc acetic acid, means NO bond breaking, not the attacking of this imine bond. So they used lithium aluminum hydride for performing two reactions. One is attacking of imine bond, again another is NO bond breaking. But in this case, in the current case, we need only NO bond breaking. That's why they use zinc acetic acids. So these are the in this way you can learn, and you will learn so much reagent use of reagents. So yeah, that is the product. If we see the options, the hydrogen and pH should be same stoichiochemistry, but here bicyclic is there, so these two are not the correct product. So bicyclic ring will break. So NET is there, it is also not the correct product. NH and this H and this pH should be same stoichiochemistry. So yeah, this hydrogen is above, means this bond should be below, and H and this hydrogen should have same stoichiochemistry. So option D is correct for this reaction. Now move to the next questions. So this is the diazocarbonyl compound we all know, and we all know that diazocarbonyl compound in presence of metal like copper acetate or rhodium acetate, it will form carbene. And see, let's see the simple questions. So rhodium acetate in presence of benzene solvent, rhodium acetate, or you can use copper acetate also, then it will form carbene. After releasing nitrogen, a good leaving group, it will form carbene. Carbene is an electron deficient species. Lone pair of this oxygen will attack this carbene to form a, again see, this seems a 1,2 dipole, but if we break this bond, positive charge will be there. In this way we can say this is a 1,3 dipole compound, or it is called as carbonyl halide. Now this carbonyl halide or 1,3 dipole will react with alkyne. If there is presence of alkene or alkyne, obviously electron deficient, it will take part in cyclodaddition reaction, that is 1,3 dipolar cyclodaddition reactions to form this kind of product. So 6-member ring along with some 5-member ring, 1, 2, 3, 4, 5. So 6-member along with 5-member ring, and the 5-member ring formed between this methyl carbon and the carbon adjacent to the carbonyl carbon. So this is not the correct options. 4-member ring, 6-member ring, this is also 4, 6. 6-member ring along with some 5-member ring, bond connectivity methyl and the carbon adjacent to the carbonyl carbon. Yeah, C is the correct option. If we see the D, there is no 6-member ring along with some 4-member ring. So the correct option for this reaction is C. This is a simple reaction. One point I have to mention, that is the, if we used copper acetate, copper salt also, then this carbene will form. So if there is diazocarbonyl compound, then in presence of rhodium or copper metal complex, then it will form carbene. Now since carbene carbon is electron deficient, this oxygen lone pair give electron to this carbene, now form a carbonyl halide. It is a also 1,3 dipolar compound. It will take part in cyclodaddition reactions with some alkene or alkyne. After that we obtain this kind of product at last. So next move to the next, let's move to the next and last question for this videos. So yeah, see, this is a Norbornene carbonyl compound. Is this compound name is something like of norborneol or norborneone kind of molecule. If OH is there, means norborneol. So this is norborneone kind of molecule. So I forgot the name of this molecule. And on hydroxyl so group is there. So these are the reagents: lithium aluminum hydride, ether, triphosgene, K is methyl iodide, lithium aluminum hydride. So yeah, these are the options. Let's discuss the mechanism in details. So yeah, in the first step you have to carefully see the first step. See, we are using lithium aluminum hydride ether. Here lithium aluminum hydride perform three reactions. If you can remember the lithium aluminum hydride use of the second questions, that is the attack of amine carbon and then NO bond breaking. See, in this case lithium aluminum hydride do three works. One is reduction of this OH carbonyl to alcohol. So H minus attacks from the less hindered side. The top side of this molecule is hindered, so H minus attack from the below side. First H minus attack from the below side, it's become OH. That is the one reaction lithium aluminum hydride perform. Second one is it will attack this amine carbon to form NH and OH should be there. Likewise, just give me a few seconds. Lithium aluminum hydride amine carbon attack become NaO. Again lithium aluminum hydride do another work, that is NaO bond breaking to form NH and OH. In this case the first step only, lithium aluminum hydride perform three works. One is reduction of carbonyl to alcohol, obviously H minus attack from the below side. Then H minus from lithium aluminum hydride attack from this amine carbon, it's become NH and that is NH OH bond will be there. Then lithium aluminum hydride break this NH OH bond just to form NH2. So OH will leave. Same reactions, question number 2, we saw there lithium aluminum hydride attack the amine carbon, then NO bond breaking. Similar case here. Here extra one work is reduction of carbon compound to alcohol. Now we are getting this product after first step. Then KOH is there. It will abstract this OH hydrogen to form O minus. Now this is the trifosgene. We all know in the question only name is given trifosgene, structure is not given. So we all know phosgene, that is COCl2. So COCl means phosgene. This is called trifosgene. If we break this compound, it will form 3 moles or 3 equivalent of trifosgene, 3 equivalent of phosgene. See, if this bond will break and this Cl minus release, then this whole molecule is phosgene. Just release on Cl. Again this whole molecule, if we release on Cl from this CCl3, become phosgene. And this Cl and this Cl, this 2 Cl, if attack with if attach with this carbonyl carbon, then that is another phosgene molecule. So this molecule is, if it breaks, it will form 3 moles of phosgene. That's why it's called trifosgene. 3 molecule of phosgene. So now this O minus attack this phosgene, this carbonyl carbon, it will break like this. It will break, this bond will break on Cl minus leave. So one phosgene along with on Cl minus leave from this molecule. Again KOH abstract one hydrogen from NH2 group. This N minus attack this carbon. Again this bond will break and another molecule of phosgene along with a Cl minus will release. So after that we are getting this kind of product. Now we are using KH. This will abstract hydrogen from this NH group and this minus that will attack this MEI to form NMe. Now again we are using lithium aluminum hydride. In this case some harsh condition means reflux and 18 hours time. So yeah, now we all know amide and ester will reduce via lithium aluminum hydride. Amide reduced to amine and ester alcohol. So lithium aluminum hydride first, in presence of lithium aluminum hydride, first this amide will reduce to amine, means this CO bond just becomes CH2 neutral amine. Then this bond will break, this CO bond will break to form OH and NMe2. NMe one is there. After reduction this become CH2. Again this bond break, OH and CH2 becomes CH3. This is the one way. Another way you can think about that, if lithium aluminum hydride oxide this ester molecule, see in this molecule two functionality you can assume. One is this amide functionality. If you see in this way, this is a A star functionality. See, A star functionality, this is a amide functionality. You can think about the this A star become alcohol. So now A star become alcohol means this OH and this NMeCOH means amide. After reduction, A star become alcohol and this become amide. Again this amide in presence of lithium aluminum hydride become amine. So this MENCOH become NMe again Me. So you can think about two way, but in the paper from where we collected this data, they showed like this: first amine reduced to amide reduced to amine, then this bond will break to form OH and NMe2. And I think many of you already know this molecule. This molecule is NMe2OH, is known as 3-exodimethyl amino isoborneol. So it is named as DAIB. This is minus DAIB. It is a efficient asymmetric catalysis in current days. Efficient asymmetric catalysis for reducing of carbonyl compound to for reduction of carbonyl compound. So DAIB 3-exodimethyl amino isoborneol. This is a efficient asymmetric catalyst for reduction of carbonyl compound asymmetrically. So yeah, I think in the maximum question we used lithium aluminum hydride for reductions, for imine bond breaking. So yeah, and maximum case we saw there 1,3 dipolar hydrogen reactions, sigmatropic rearrangement. So in this way we learned some reactions, that is sigmatropic rearrangement 2,3,3,3, use of some reagents, and this is a asymmetric catalyst synthesis. This is the asymmetric catalyst synthesis. In this way we can synthesize this asymmetric catalyst DAIB. So and the options for this C, NMe2OH. So NMe2OH should be there, Na is MECO. So these are not the correct option. Option D is correct for this reaction. So yeah, that's all for this video. So I think all of you understood what I just trying to show you, the mechanism, the use of some reagents. If still there is some doubt, please comment in comment box so that we can know, and we will try to solve your doubt as much as can possible. So if there is any mistake, yeah, I again admiring that maybe there is some mistake in our discussions, drawing mechanisms. So please let us know. So I hope this videos, that is discussion or solving questions from organic chemistry, will help you a lot to improve your organic chemistry question solving power for upcoming competitive exam. And I believe that this video will be very helpful for all of you. So yeah, thank you for watching. So stay safe, stay healthy, and also stay tuned, because lots of videos containing various concepts in chemistry are on the way. So we will upload lots of questions in our upcoming videos. And yeah, one point, that is, please see the chemistry concept booster series. So we already uploaded that is including this video 40 questions maximum from organic and physical chemistry. So please see those chemistry concept booster series. So at least that will help you a lot to improve your concepts in chemistry. So yeah, thank you again. Bye.